Okay. So we'll continue from where we left off last week, where we were considering the different factors that influence the position of peaks in NMR spectrum. So last week we considered the intramolecular factors, which we described as the inductive effects, magnetic anisotropy, and hydrogen bonding. So today we look at intermolecular factors. So this is intermolecular factors. Okay. And we find that hydrogen bonding also takes place between molecules, and the effect on the protons involved, the peaks for the protons involved, is similar, which is the shielding, and the chemical shift increases. However, the difference between intermolecular hydrogen bonding and intramolecular hydrogen bonding is that the concentration has an effect on the chemical shift observed when intermolecular hydrogen bonding is involved. So a higher concentration leads to to a shift or to an increase in the chemical shift between molecules is the solvent effects. And the most prominent of the effect is due to polarity of solvents. It has been observed that the protic solvents are able to hydrogen bond with the analytes, which then shifts the chemical shift to higher values. In addition, if the solvent has magnetic anisotropic effects, then this interaction can affect the chemical shift of analytes. Another factor is the concentration and temperature. So we have already mentioned that concentration can affect the chemical shift by either increasing or decreasing hydrogen bonding, and therefore the chemical shift. Temperature similarly can affect hydrogen bonding. Higher temperatures reduce hydrogen bonding, while lower temperatures increase hydrogen bonding. There is also another factor known as van der Waals deshielding, and this occurs in compounds that may have bulky groups, and these bulky groups are able to hinder the electron clouds. So this can cause temporary deshielding, and therefore a decrease in chemical shift. And finally, some impurities, paramagnetic impurities, if they are present, can cause a different chemical shifts, which are known as paramagnetic shifts. So these are much more difficult to identify because the relationship is complex. Good. So those are the intermolecular factors that are. Let us now look at an NMR spectrum and various observations that are used in the determination of structure. So we mentioned that NMR is mainly used for identification of compounds. So we need now to be able to apply what the product of NMR spectrometry to achieve the goal of identifying. The spectra usually depends on the strength of the polarizing magnetic field. And when the low energy or the weaker spectrometers produce peaks which are usually corresponding to the number of chemical environments. So we'll see for the same compound when different spectrometers are used, which can resolve small differences in terms of the differences between the resonance frequencies. So for the weaker equipment, we normally get single peaks for each chemical environment. And for illustration purposes, we have a spectrum of ethanol taken in a weak spectrometer. And ethanol has 3 chemical environments, and we are able to see the 3 peaks. In addition, we have some sigmoid curves on this spectrum. So these sigmoid curves are actually integration lines. And these integration lines are indicative of the intensity of absorption. So the height of these curves, if you measure that height there, so that height in whatever units of measurement of length, like millimeters, would correspond to the area under the peak. Okay? So the importance of that is that the area under the peak or the area under the curve is proportional to the ratio of the protons responsible for that peak. So if you take these measurements, okay, you take these measurements in terms of length units, and you calculate the ratios that corresponds to the ratios of protons responsible for that, for the individual peaks. Okay, so using that, then it is, you still gather more information with regard to the possible chemical composition of the compound. So if you have a question, you just unmute and ask. I'm not able to monitor the chat. Okay, so this is the same spectrum, the same compound, but now taken with a spectrometer with a higher resolution. And what we observe is the splitting, okay, micro splitting of individual peaks into sub peaks. So in the previous spectrum, we just have a single peak corresponding to a chemical environment. But in the second spectrum, we have a splitting, okay, of the single peaks in the same chemical environment into smaller subpeaks. So this is as a result of what is known as spin-spin coupling. And it is due to the coupling of protons which are in close proximity in terms of distances or separation within the compound through bonds. Okay? And we could illustrate that by looking at different compounds between hydrogens. You can have hydrogens which are connected to the same carbon. Okay? You can also have two hydrogens which are on neighboring carbons. So those are known as vicinal hydrogens. Now, in most cases, in most cases, geminal hydrogens will be in the same chemical environment and they will resonate at the same time. So they will give you a single peak. Vicinal hydrogens, however, may be in different chemical environments. And when the separation in terms of their resonance frequency is significant, then they resonate at different frequencies. Different hydrogens are able to couple and split the, uh, the spectrum of each other. In other words, if you consider a case of dichloroethane, you can see that we have hydrogens which are in two different chemical environments. Now we have this hydrogen, okay, which is attached to the carbon bearing the two chlorine atoms. We also have these three hydrogens which are bound to the other carbon, okay? So in essence, we can say that these two chemical environments will produce two peaks, okay? Two major peaks in the NMR spectrum. And because the differences in chemical shifts of these two chemical environments are quite significant, when the methane hydrogen is resonating, the other three hydrogens will not be resonating, okay? So they can be in the higher energy state or lower energy state. And the different combinations of those energy states for the three hydrogens then yield a net magnetic field, which is different depending on the excitation state of the other three hydrogens. So if we were to maybe illustrate the different possible combinations of the energy states of the three hydrogen, we can have these three different conditions, okay? You can have a state where only one of the hydrogens is in the lower energy state and the other two are in the higher energy state. use that. So in that case, irrespective of whichever is up or low, okay, then that is one codation. You can also have a codation, okay? So all these are illustrating that. So all these are similar, right? So two are up and one is down. Similarly, these are the same, okay? Then you can also have another situation where all of them are in the higher energy state. That is one condition. You can also have another, you can see one first. You can also have another situation where all of them are in the lower energy state. This one can split it down the middle. So on the left side, we have two in the high, two in the lower energy. One possibility where all of them are up. You can down, okay, 1, 2, 3. You can have three possibilities where two are down, one is up. So 1, 2, 3. And you can have only one combination where all of them are low energy state. So in terms of possibilities of getting the different conditions, we get 1, 3, 3. This hydrogen will experience magnetic influences from the vicinal hydrogens, but those probabilities are in the ratios of 1, 3, 3, 1. That affects the effective magnetic field felt by the hydrogen from the polarizing magnetic field, and therefore the resonance frequency, this is 1, 2, 3, 4. Okay, the four different combinations of those sub-peaks, okay, will be in the ratios of 1, 3, 3, 1, which are the different combinations of possibilities of the energy states of that hydrogen. So let's go back here. So if you look at, let's make that formula. Okay. So we have CH3. Those are the three hydrogens. We have the CH. We have the OH. Okay. So we said that we can first ignore the OH, okay? Because we said the chemical shift normally depends on the concentration. As we have mentioned, the intermolecular influences. However, we know that ethanol has a CH3, which will be the most shielded. So we expect that this peak, okay, the main chemical environment here, is due to CH3, the methyl protons. Okay? And we expect this to be due to the methane protons. Okay? The CH. So if you look at this peak, okay, the main chemical environment, which is at around 3, due to the methylene, it has been split into 4 subpeaks. 2 in the middle are large, the 2 outside are smaller. But if you look at the heights, okay, of the 2 outer ones, they are the same, and the 2 middle ones are the same. And that is as we would expect, that this outside one is the same, the middle ones are also the same, but the relative heights are according to these ratios that we have counted here. Okay, so anytime you have a methylene group which is interacting with hydrogen, then you always get this splitting ratio of 1, 3, 3, 1, giving you 4 different chemical environments for the coupled hydrogen, but also giving you the intensities of the peaks that are resulting from that splitting. So using the same arguments, then we see that the methylene proton peak will be split by the methyl proton peak is going to be split by the methylene protons. Okay, and what are the possibilities? You have 2 hydrogen, 1 down. Okay, you can also have the other a reverse of that. This one is down, this one is up. Okay, so that combination is similar. Okay, you can also have all of them up. Okay, both the methylene protons in the higher energy state. That is only one possibility. You can have both of them down. Okay? That's also only a single possibility. Okay, so if you count the possibilities, so this is 1, these are 2, 1, 2, and this is one possibility. So we get 3 subpeaks. The ratios of the subpeaks are 1, 2, 1. So you see the 2 outer ones are almost the same. Okay. Okay. So showing that this peak, okay, is being split by 2 vicinal protons, and methylene protons, if coupled to another peak, will split that peak in the ratio of 1 to 1. Okay. Any questions? Okay. So one could ask, why is the hydrogen, which is also 3 bolts away from the methylene hydrogens, not coupled? So the explanation is that these hydrogens are exchangeable hydrogens. So the residence time on this oxygen is quite small, such that you can, it's actually not having enough time to split. Just a minute. So this hydrogen, the hydroxyl proton is not coupled to the methylene proton because the residence time is short, and to the vicinal hydrogens because of the short residence time, and therefore not splitting the hydrogens. The methylene protons will not split the peak from the hydroxyl group, and therefore it appears as a single peak, okay, with no spin-spin coupling. So what we are get is a first order coupling, which we have outlined. And when you have no coupling hydrogen, that peak as a singlet. Okay. When you have one proton, we get splitting of the peak into two. Okay. And we get a doublet. You can see how the doublet results, because that hydrogen can be in the upper energy state or lower energy state, and therefore the splitting of these peaks, of these protons peak. If we have two hydrogens which are coupled to the hydrogen, then we have said we get the splitting into three with a ratio of 1:1. So we get three subpeaks in the ratios of 1:1. And then if you have three hydrogens, like when you have a methyl group, then the split is into four, and the ratios are 1:3:3:1. So you can see what we call the past cos triangle. It follows that pattern. Okay. When you have more than three hydrogens coupling, the splitting is usually described as a multiplet. Okay. So one hydrogen gives a doublet, two hydrogens give a triplet, three hydrogens from a methyl give a quartet. More than that. Now, uh, when we talk of splitting, it means that we have differences in terms of resonance frequency coupling. The difference in those resonance frequencies result usually constant, and they are given the identity of J constant. So irrespective of the equipment, if two hydrogens are coupled, that that value will always be constant. The only difference is that they are spectrometers, but not resolved in weaker spectrometers. But J is always a constant value. Any questions so far? Okay. So the first scenario we discussed is this first order coupling, where are quite different and the peaks, the peak intensities appear equal. Okay, so if you look at this, we are saying that the two outer ones are equal in height, the two middle ones are equal in height. However, if you look clearly, you can see that there is a slight difference. The ones to the outside are smaller, and that is as a result of what is known as second order coupling. And that's what we are illustrating here, that as the two chemical shifts between the coupled hydrogens decreases, okay, then the second order coupling occurs or is more clear. And the outer, the splits on the outer side of the peaks shorten or decrease as the middle ones increase. And this happens until the two chemical environments are the same, where the coupling collapses. So if the differences between the two chemical shifts are large, for example, more than 2, then second order coupling is absent. When the chemical shifts are smaller, then outer intensities decrease while the inner intensities increase. So that is an illustration of second order coupling. And they are all, there are many types of descriptions uh, showing the different levels of coupling. So here we have isopropanol, a spectrum of isopropanol. And we see that we also have uh, three chemical environments, a methane proton and a hydroxyl proton. And we can see that the methyl protons a single peak, but because of the methane proton, that peak has been split into two. The middle singlet is due to the hydroxyl group, and you can see that if you compare that hydroxyl group, the chemical shift of that, and it is quite low. Okay, so that's why we say that the OH rocket, and you need a way of confirming it is due to the hydrogen. So due to the hydroxyl proton. So we can ignore that for the time being. But you can see that we have a very short peak, but split so many times. Okay, and this is due to methane hydrogen. Okay, that is the split by protons and the other three methyl protons. So if you look at that, if you take n be the number of protons that are splitting or that are coupled to a peak, then you expect to get n plus 1 subhydrogen, you get an extra peak. When you have 2, then you get 3 subpeaks. Okay? When you have 3, you get 4. And when you have 6, then you would expect a similar trend. Okay? So this this peak due to this hydrogen, the methane hydrogen, is split into 7, making it a very weak signal. Okay? And you can describe that as a multiplex. Any questions? So let's now look at a logical stepwise process that one might go through while trying to either identify a molecule given a spectrum or to assign peaks. Okay? To assign peaks given the structure and the spectrum. So it depends on whether the structure is known or unknown, and then using logical thinking in order to confirm the structure as given, or to come up with a structure of an unknown. So the first consideration, if you have the molecule, it is to look at the molecule structure and then look at the chemical environments, okay, which you can illustrate by drawing around them. Okay, like in this case, we have propanol. So using different shades of color, you can draw, or once you draw circles around them, you can label them using letters or numbers. Okay, so that helps you to refer to them. So if you look at propanol, for example, we have 4 different chemical environments. And therefore, if we are to get an NMR spectrum from this compound, we would expect 4 major peaks. Okay? Of course, if major peaks to be split due to coupling. Now, when you look at an NMR spectrum, you get major peaks. If now you only have the spectrum and you're expected to come up with the structure of the compound, the number of peaks, major peaks, gives you the chemical environments. However, if you have the formula, you can of the compound by trying to find whether there is unsaturation in the molecule. So you can do this calculation that you learned in your chemistry, where you can determine the extent of unsaturation. And this is simply by using this equation, where you could use the number of carbons and the number of hydrogens or halogens that are present to determine the elements of unsaturation. And what you'd find is that in case you have 4 elements of unsaturation, then that is more indicative of a benzene ring. Okay, so I will not go deep into that because it's something you have done previously and you can always take it up. Okay, but that is a formula: 1 plus the number of carbons, you less the half value of the number of hydrogens and halogens. If you had a nitrogen, then that is equivalent to half a carbon. Okay? So if you look at the the spectrum, besides the number of peaks, you also get information on chemical shift. Just a minute. So the NMR spectrum gives you information on the number of peaks as well as the chemical shift. So the number of peaks give you the number of chemical environments. The chemical shift tells you about the environment itself. Okay, and that can help you to uh, determine the type of protons present in that compound. So you can either have data or you can have charts like the one we have here, okay, giving you a general chemical shift for the different types of protons. So in the lower chemical shifts, we have the alkanes, okay, where there is complete saturation. When electronegative groups are introduced, then the chemical shift moves to higher values, inductive effects. Okay, so like if you have a hydrogen attached to attached to that's a methyl group attached to a carbonyl, for example, then you get the chemical shift increasing. When you have a hydroxyl group attached to the same carbon as the hydrogen, we also have that effect resulting in an increase in chemical shift. Similarly, remember we talked of magnetic, so such a chart now gives you an idea. When you see a peak in a certain region or a certain value of a chemical type of a appearing between, let's say, 4.5 and 7, an alkene proton, but also to some extent an aromatic proton or a proton attached to a carbon also bearing an electronegative element. So looking at the general position of the peak, then you can have an idea what type of hydrogen it is. So the general areas are the alkenes, the aromatic, and then the ones attached to carbonyl, carbonyl carbons, okay, the aldehydes, the esters, etc. So in most cases, you get those ones on the higher side will be either directly attached to the carbonyl or hydrogen bonding is involved. Right? So the next consideration is, of course, the splitting pattern, which gives you the number of protons attached to the maybe around this region. Then if you look at the splitting pattern, it's probably split into a doublet. That means there is only another, a single proton coupled to it, okay? So by looking at the splitting pattern, it gives you an idea of the connectivity. Then, of course, the other consideration, we have looked at the chemical shift, we have looked at the splitting pattern. The other thing to consider are the ratios of intensities. Okay? The ratios of intensities, that is the integration peaks or the integration lines. By looking at those, then you are able to work out the possible ratios of the hydrogens present in the molecule. So the process, therefore, would involve looking at the spectrum, deciding on the possible fragments, okay? And then logically trying to connect the fragments into a whole molecule. We also need to remember that you can have what are known as barrier groups. So these are groups which do not have a hydrogen attached to them, and therefore there is no coupling. For example, you can have uh, see that. Okay, so we have this compound which is an ester. Somebody tell us how many peaks we expect to get from this compound. Just unmute and tell us.
2 peaks.
Yes, we would expect to get 2 peaks. And how would the splitting pattern be? Splitting pattern. We get singlets, doublets, triplets, or quartets.
We have since we have two peaks into chemical environment.
Yes.
So we'll expect then in the two environment we have three hydrogens. So
Mm-hmm.
we'll get a triplet.
Mm-hmm. Okay. Another suggestion?
I think it will be a quartet.
Mm-hmm. Okay. Stanley says a quartet. Another suggestion? Okay. So what we have here are two methyl groups, which are separated by a barrier group. Usually, for spin-spin coupling to occur, it will most often happen in vicinal hydrogens. Okay. So these two methyl groups are too far apart for coupling to take place. So what we get are actually two singlets, okay? In this particular example, are too far apart, respective methyl groups, two singlets with integration lines which are equal in height, okay? Because we have three hydrogens in each chemical environment. So in this case, we have this group here that we are calling a barrier group, which is preventing the coupling of the hydrogens that would normally occur. Any question? Any clarification that is needed? So this is just for revision purposes. I'll send you a number of examples. Any problems, you can always get back to me. So what is the effect of using a spectrometer with a stronger magnetic field on one frequency of absorption? Someone quickly answer that. Using a spectrometer with a stronger magnetic field on frequency of absorption. In other words, what is the effect on the resonance frequency? Does it increase or decrease? Someone? There is only two choices. There are only two choices. Just pick one.
A stronger,
And
a stronger magnetic field increases the frequency of absorption.
yeah, that's correct. What is the effect on chemical shift?
It will decrease the chemical shift.
Mm-hmm. Another suggestion? Yes, Bruce. Bruce Jero, you there?
Yes.
Yes. What will happen to the chemical shift? What will happen to the chemical shift?
I'm not sure.
So all of you, majority of you logged in on the earphone mode. Don't want to speak. Mutuma Morris. Morris, you're there? Okay. So Clifton says it will remain constant, which is correct. So we say that chemical shift is one way of standardizing the output of the equipment so that we are able to compare. So the chemical shift is not affected by the strength of the magnetic field produced by the spectrometer. And what about the J constant? What will be the effect on the J constant? Benson, Juguna?
I think there'll be no change in the J constant.
Okay, that's correct. We have mentioned that J constant is a constant strength of the polarizing magnetic field. Is an intrinsic property of protons. So good. So that is those are just a few examples.
Excuse me.
Yes.
Regarding the barrier groups,
Yes.
which just restricted to the ones I should mentioned, the ketones, the ester, and the ether.
It's basically any group that does not have a hydrogen attached to it.
So
you can have a simple carbonyl group, you can have a sulfur, okay? For example, you can have, for example, and then another methyl, okay? So any group that is separating groups which have coupling to occur. Okay? So you may not exhaust the examples, but just looking at the structure, then you get an idea. Okay, these are a carbonyl. Let's say which other group? A simple oxygen. Okay, for example, if it's an ether. So those are simply barrier groups. Any which is preventing coupling, okay? Or any group which is increasing the separation between the hydrogens, thus making them non-vicinal. Does that answer your question, Stanley?
Yes, yes.
Okay.
Excuse me.
Yes.
How will the strength of the magnetic field affect the resolution of the spectra in NMR?
Okay. So what happens is that when you increase the strength of the magnetic field, the separation. Okay? Remember we said that yes, so what we said is that the resonance frequency is directly proportional to the strength of the magnetic field. You increase the frequency. So what that does is that where you had two, let's say, that is the difference between uh, two peaks is 1 hertz, okay? When you increase the strength of the magnetic field, that, okay, but that enables the equipment to show you that these are actually two peaks. In a weaker instrument, a lower polarizing magnetic field, you are not able to resolve those peaks into two different peaks. But when you increase the magnetic field, you increase the differences in terms of hertz. Okay, but when you convert, value will not be will be uh, 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 constant. In other words, that is why we actually use the chemical shift, because if you look at the absolute values of frequency, then it depends on the strength of the magnetic field. But when you convert to chemical shift, that difference is not observed. However, a stronger magnetic field allows you to be able to tell apart two frequencies which are too close to be. Does that answer your question, Julius?
Yes, yes, yes. Thank you.
Okay. So if there is no other question, move to something else.
I wanted to ask.
Yes.
When you have a molecule like methanol, now does it mean now it will have two peaks, only two peaks because of the barrier group, the oxygen?
Yes, that is correct. You will have two peaks, one due to the methyl group and one due to the hydroxyl group.
Okay.
Any other question? All right. So then let's move to carbon-13 NMR spectroscopy, which we alluded to when we were introducing NMR, and the isotopes of carbon which are NMR active. Carbon-13 is going to be NMR active. The other two will not be active. Carbon-12, which has 6 protons, 6 neutrons, 2 even values, giving you a spin of 0. Okay. Similarly, carbon 14 with 6 protons, 8 neutrons, 2 even values, also NMR inactive. So only one isotope of carbon is active. Now, if you look at the proportions of carbon, which is NMR active, it's about 1%, which occurs naturally. But if you look at the proportion of hydrogen, okay, so you get 99.9% of hydrogen is NMR active. Only 0.1% is not active in the same region, but it is also, however, NMR active. So this deuterium will not resonate at the same frequency as the hydrogen. So what that tells you is that for every hydrogen atoms present in a certain position of a molecule, 99.9% will be absorbing the frequency. But for every 100 of carbon, only one will be absorbing NMR radio frequency. Okay? So that means that a higher sensitivity equipment is required to carry out carbon NMR spectroscopy. Okay? So, and that is why we say that wave method with hydrogen, a special technique which we called the free induction decay or the pulsed NMR technique is required to carry out carbon-13 spectroscopy, which allows the addition of spectra and therefore increasing the sensitivity. Okay? Requires pulsed technique. In addition, we'll see another process that is needed, known as carbon-13 NMR. You have said only the carbon-13 is NMR active. Okay. Then we also find that carbon-13 has a weaker magnetic moment in terms of, we say that the intrinsic property, intrinsic tendency of the atom to respond to radio frequency is different. So carbon-13 happens to have a weaker magnetic moment compared to hydrogen. So we have talked of 3 things that make it necessary to use a more advanced technique to carry out carbon-13. First, if carbon isotope is magnetic moment and coupling to hydrogen splits the peak, therefore, which is already weak, and therefore making the intensities very small. And that requires special techniques, which we shall look at a few. Okay? So, in addition, due to the smaller proportion of NMR active carbons, we rarely find carbon-carbon coupling In other words, it's harder to find two carbon atoms which are NMR active being attached split to be able to split the peaks of each other. Okay, so we do not usually have carbon-carbon coupling like we find in hydrogen-hydrogen coupling. So carbon-13 NMR therefore require spin decoupling conditions. And what is spin decoupling? It means that in carbon-13 NMR, the hydrogens are irradiated with a strong or with a high intensity radio frequency close to the frequency of resonance of hydrogens. While additionally, that if, for example, you are using 2.35 Tesla equipment, then the hydrogens will be resonating at around 25.2. So the with a high intensity radio frequency at around 100 megahertz. So that maintains a lot of them in the high energy state, which now does not split the carbon or does not couple spectrum where the hydrogens are not irradiated. Okay, what type of a carbon or how many hydrogens are attached to a particular carbon of them that we will mention in due course. So looking at the spectrum of carbon-13, we find that there are not very many types of carbons. So you can have carbons which are attached to carbons, carbons which are attached to electronegative elements. You can also have alkene carbons or aromatic carbons. And then we have the different regions. The alkane carbons will be in the lower regions, just like you would expect, because of the weaker inductive effect. So the same factors that influence the position of the chemical shift for protons similarly affect or influence the chemical shift of carbons. Okay, so the alkane carbons, the saturated carbons, will be lower. The shift for protons is for carbons is much wider. It ranges between 0 and 220, while the chemical shift for protons is between 0 and 15, the maximum. Okay? So for saturated carbons, between 0 to 65. That is the usual range, 0 to 70, 65 to 70 there. So if you see a peak in a carbon spectrum between 0 and 65 to 70 there, it tells you that that is a carbon which is saturated. If the value is closer to 65 to 70, then you are thinking of a carbon attached to an electron. Around 20 to actually 30, it's more of a carbon attached to other carbons. Now, when you move to the unsaturated, okay, the alkene will be almost within the aromatic region, but the aromatic region is wider because of the different possibilities. But the aromatic, anything above 100 is actually aromatic. Okay, between 100, okay, between 100 and 130 will be benzene. Okay, but if you make other substitutions that enhance the shielding effect, then that region is extended. So anything either aromatic or an alkene. Then anything above 160, we have the carbonyl carbon. Okay, the S lower than the aldehyde. Okay? So the aldehyde carbon or the ketone carbon will be much higher, anything between 190 to 220 will be just the plain carbonyl, not attached to the electronegative or the lone pair containing groups. Okay, so for example, this nitrogen can donate its electrons to the carbon and thus lowering the deshielding effect. Okay, the same with this oxygen, which has a lone pair of electrons, it can donate to the carbonyl, reducing the positive charge on the carbon. So those are basically the 4 different regions you'd find the carbons. So there is less overlap, and there is no splitting in carbon-13 NMR. There is no carbon-carbon peak splitting in carbon-13 NMR. So let's see how now we use the carbon-13 spectrum. So we are saying that you usually get any peak that you find in a spectrum is going to be specific for each chemical environment of the carbon. Usually, the height of the carbon peak is equivalent to the ratio of that type of carbon in that compound. So in carbon 13 element is usually configured to give the heights of the peaks to be proportional to the ratio of of carbons present in the molecule. So like in this case, you can see that we have 3 peaks which are equal in height, indicating that the ratios of the carbons are 1 to 1 in all cases. Okay? But if you look at this compound, we have 2 peaks showing that we have 2 chemical environments. The high ratios of carbons responsible for those peaks is 1 to 2. Okay? You can also see that the chemical shifts are within the expected regions. we said the alkane carbons will be close to 0. So it will be saturated carbon either attached to other carbons or to electronegative. And you can see that this peak, which is higher, is due to the inductive effect of the hydroxyl group or the oxygen of the hydroxyl group on that carbon, which groups are close to 20. In this condition, in the other compound, which is propanol, we see that we have 3 peaks. So each carbon is different, is in a different chemical environment. And we can see that the methyl group is farthest from the oxygen, and therefore minimal effect of that hydroxyl group is experienced by that methyl group, and therefore there is extensive shielding. So if you compare, this methyl group is about 28 compared to this one, which is at 10. So you can see the effect of increasing the separation of that methyl group from the inductive effect of the hydroxyl group. So that has minimal effect on that group because of that distance. So that is basically how a carbon-13 NMR spectrum looks like. You can get the chemical shift from them. You can get the possible ratios of the carbons in each environment. So here we have another spectrum with 3 peaks. One peak is between 0 and 10. The other one is just below 40. The other one is just above 200. So the information we gather from here, just by looking at that spectrum, is that we have 2 unsaturated carbons, or 2 saturated carbons, and possibly 1 carbonyl carbon. Now that we have the formula, the possibility is that 1 is carbonyl. So we already know that we have a CO group, okay, which we can assign to that peak. So we are left with 2 carbons and 6 hydrogens. So that probably tells us that we have a CH2 group and a CH3. And why are we saying that? Because if we had CH3, then they should be in the same environment because we only have 6 hydrogens. So the only remaining group is a hydrogen somewhere. So in essence, we are saying that just by looking at this 3 spectrum, 3 peaks, and seeing that we have 3 carbons in the compound, 1 is a carbonyl carbon, so we can do a CO group. Then the other 2 carbons cannot be the same, okay? So the only way to have them different is to have a CH3 and a CH2. And then we have a hydrogen. So we have 4 different fragments, which give us a complete elemental composition of the compound. So in how many ways can we attach this group? Obvious one is to connect the hydrogen there and that carbon to that CH2 and that CH2 to that carbon of the compound. If you try any other connectivity, then you get possible to explain each of these carbon peaks that are in this compound. Any question on that? Okay, so if there's no question, we can try to see another example. So we have another structure here, another spectrum here. We are given the chemical formula and the NMR spectrum. Okay, so we are saying that we have 4 peaks for the carbon-13 spectrum. And when we look at the chemical formula, we have 8 carbons. Since the peaks are of equal height, that probably means that each peak is due to 2 carbons. So we can say those are 2 carbons and 2 carbons. Okay, that's looking at the intensities. Then we look at the chemical shifts. Okay, so we see that we have a chemical shift which is about 19 or 18. Okay, so that must be alkane carbons, and there are 2 of them. So they may be linked or they may not be linked. Let me not link. Let me just put them as carbon. Then we look at the other spectrum, the other 3 peaks. They are above, they are between 120 and 140. That tells us probably is an aromatic system. So by looking at that, a benzene ring system. Okay, because of the chemical shifts and the fact that we have 6 carbon atoms. We can confirm that by calculating elements of unsaturation. Okay, so the elements of unsaturation is 1. We add the number of carbons, which is 8. We subtract the number of hydrogens, which is 10. We do not have any other group, and we divide that by 2. So that gives us 4. Okay, so this structure or this chemical formula tells us that the compound has 4 degrees of unsaturation, which can be accounted for by the ring system, by the aromatic ring system, as 3 double bonds, okay, which accounts for 3 of the degrees of unsaturation, plus the ring structure is another degree of unsaturation. So anytime you see a compound with 4 degrees of unsaturation, you are probably thinking of a benzene structure. Okay, So in essence, we have now accounted for the 4 degrees of unsaturation by having a ring structure. We have accounted for the 6 aromatic carbons and the 2 alkyl carbons. So let's now think about what kind of substitution would give us 2 carbons which are, or the ratio of the aromatic carbons to be in the ratio of 2 to 2. Okay, is it a single unsaturation, a double unsaturation? And if it is double, using these alkyl groups, alkyl carbons, then what are the relative positions of those substitutions? So we can draw all the possibilities. Okay. We can draw all the possibilities of the different substitutions and then working out which of that we have. So if we look at the first compound, we get 4 different chemical environments for the carbons, okay? That means this carbon which is substituted with a methyl group and this carbon substituted with a methyl group are equivalent because they are the same distance from all the other groups when you consider each of them separately. Then the 2 carbons which are ortho to the methyl groups and the 2 carbons which are meta to the methyl groups. So what we see is that these first compounds gives us a ratio of 2 to 2 for the aromatic carbons, and then 2 methyl groups, which are equivalent. So in essence, this particular compound corresponds nicely to the spectrum that we have. If you consider the second compound, where you have the 2 methyl groups attached meta to each other, then the aromatic carbons are in 4 different environments, which does not correspond to what we observe in the spectrum. In the third case, the methyl groups are parallel to each other, which makes 2 chemical environments for the aromatic groups, aromatic carbons, which violates the observation. Similarly, if you just have one substituent, then we get the alkyl carbons are different. Okay, they would be in different environments, which we are not observing. And similarly, the aromatic carbons are in 4 different environments, which is not the case in our spectrum. So the group or the structure that meets our current information is that structure. Okay? So we can comfortably say that the first compound there satisfies the observation of the spectrum that we have. Any questions? Okay. So if there are no questions, then let's look at another aspect of the NMR spectroscopy. spectroscopy techniques. So to gather more information from NMR spectra. There are many ways in which NMR gather more information. So some of the techniques are chemical, like we outlined previously, where we talked about exchangeable protons. And we said because of the high variability of chemical shift observed with the exchangeable protons, then a specific method is required to pin them down as to the chemical shift where they are occurring. And one of the ways is a chemical determination by using the deuterium exchange technique. And this is addition of heavy water or deuterium oxide. The deuterium exchanges with the proton, and because deuterium does not resonate at the same frequency, the peak due to a hydroxyl group or an exchangeable proton disappears from the spectrum when deuterium oxide is added. Okay? So that is one way of confirming that you have an exchangeable proton within the molecule. An exchangeable means it's a hydrogen attached to either a nitrogen or an oxygen, most commonly, but also a sulfur in some cases. Another modification is in the way NMR spectroscopy is performed. And one of the ways is decoupling. And as I explained, decoupling involves irradiating the coupling nucleus with a high intensity radio frequency that increases the frequency of conversion from low energy. That yeah. So irradiating the coupling frequency, the coupling nucleus with a radio frequency close to its resonance frequency, thus increasing the rate of conversion from low energy to high energy state. And therefore, the splitting does not usually occur under those circumstances. If the coupling nucleus is the same as the nucleus being observed, then we call that homonuclear decoupling. If the decoupling is different or the decoupled nucleus is different from that being observed, then we call that heteronuclear decoupling. Okay? But there are also cases where the decoupling frequency is slightly different from the actual resonance frequency. So that is known. So another modification is in the output. The most common spectrum is usually what we call a 1D NMR spectrum, where you just the intensity. By using applying or have a 2D NMR spectrum, correlation spectroscopy, or another one called heteronuclear correlation spectroscopy, or HETCO. So these are modifications of the NMR spectrum, and each of them has its own strengths. Okay, so like this is spectrum of the compound given there, ethyl benzene. Okay, and what we have are two axes. Okay, you can see the two axes. So if you are to plot a diagonal here, it would correspond to the 1D NMR spectrum, but now in this case, the intensities are suppressed. Then we can use this, the two axes to tell us the chemical shifts. So what we get from here is that we are able to see that extra peaks, which we call cross peaks, correspond or show us the two peaks which are coupled to each other. Protons producing this peak and the protons producing this peak are actually coupled. But we have another peak down here, okay, which is basically the aromatic protons. They are also correlated, or they are also coupled, and that's why it's appearing as a multiplet in the aromatic region. Okay, but these two are quite clear that they are coupled to each other because of the cross peaks that we observe. That is correlation spectroscopy. We also have a modification of that, which is known as heteronuclear correlation spectroscopy, which combines the carbon-13 spectrum and the proton NMR spectrum, and it shows which proton is attached to which carbon. Okay, so similarly, we have the carbon-13 peak, the spectrum, and the proton spectrum, and then peaks which indicate how the protons are related to the carbons. Okay, that is heteronuclear correlation spectroscopy. Okay. Another modification is what is known as nuclear Overhauser effect. And this is an effect which is present in some molecules where the coupled or where the coupling space. Okay. So this is whereby when observing a proton, for example, and then a coupled nucleus is irradiated, you may get an enhancement of the intensity or a decrease in intensity of the observed proton resonance. Okay, so that is what is known as the nuclear of a Hauser effect. So this occurs when the distance between the two protons is between 2 and 4 angstroms, semi-crathrate. Okay, and these two hydrogens are coupled to each other. When you irradiate one, it enhances the absorption of the other. In small molecules, nuclear Hauser effect increases the resonance intensity, but in larger molecules, nuclear Hauser effect has the opposite effect of decreasing. So there are many techniques derived from that nuclear Hauser effect, and we will not go into details of all that. We also have another technique known as depth, which means distortionless enhancement by polarization transfer. And this is used to differentiate the different types of carbons. So if you look at the normal spectrum, you get all the peaks due to the carbons, okay? But when the degree of offset is changed, then different carbons appear or disappear, or they may appear with a positive or a negative intensity, depending on the displacement. So normal carbon-13, all peaks are visible. In what is known as depth 45, the carbons which have no protons are not visible. And when is depth 90, only the carbons having one proton are visible. And when we go to depth 135, those with even number of protons will have a negative intensity, and the ones with odd protons will appear, and those without will not appear at all. So that is another technique for differentiating the different types of carbons, and therefore can be used to gain further information with regard to the structure of these molecules. So that is the same depth, but now from a specific compound, showing the application of depth to that compound. And those are the applications of NMR. Discussed the structure, elucidation, conformational studies, drug discovery in terms of target binding. Any questions? There are any questions? So then have come to the next time we look at infrared spectroscopy. I'll share some examples, and if you have any questions, you can always get in touch. Thank you and have a good day.